In the last lecture, I more than hinted, I flat out stated that there was a close connection between the entropy of a system with a large number of molecules and the number of microstates available to that system. This quantity W is the number of microstates available to the system. And here is that relation. We're going to talk about this W a lot when we get to the StatMech section of the class, but that's not for a while. So we'll leave that. This is a little undefined right now, and I bet people are kind of wondering. I mean, in the case of the box up here that we talked about last time, we can calculate what W is. Here it is. So at least in that case, it's pretty clear what it is. But you might be wondering, okay, what is it when you've got a protein in water and another protein wants to come up and bind to it? What's W in that case? Yeah, much more complicated. And we'll talk about those kinds of things. You can get at least a qualitative feeling for what W is in those cases, and you can experimentally measure what the entropy is. And here's the relationship. This is something called the Boltzmann relationship. It's something different than the Boltzmann equation. I almost said Boltzmann equation, but it turns out that there's something else called the Boltzmann equation, much more complicated than this, though not more important. This is as important an equation as you can possibly get in all of science. But it isn't called the Boltzmann equation. Let's call it the Boltzmann relationship, or the Boltzmann entropy, maybe. And it just says, what's it saying? Over here is the thermodynamic entropy, symbol S. Over here is the number of microstates available. We take the logarithm, the natural logarithm, but it wouldn't matter. We could take a different type of logarithm if we wanted. Natural logarithm is the usual choice of that W, and then we multiply by this constant called Boltzmann's constant, Kb. It has a value of 1.38 times 10 to the minus 23. And that's going to give us the entropy according to all of this. It turns out that the fact that there's a logarithm in here and the fact that there's this constant in here, both of those things really hardly matter. The truth is that this entropy over here and this W over here are really, for all intents and purposes, the same thing. S is just W on a logarithmic scale. It's just S is just a different way of representing W. S doesn't depend, this constant is a universal constant, and it's just a units matching factor. It's just making the units between this logarithm, which is unitless, and this entropy over here, which does have units. It's just making the units compatible. So the Kb really isn't doing anything at all important. If you chose the system of units correctly, you can make that Kb be 1, and there are sort of advanced level StatMech books that do exactly that, because it's a pain to always be writing Kb all the time. And you can make it go away, which shows that the physics and the behavior don't depend on Kb. So that's just a convenience factor, really. And this turns out this logarithm doesn't do much either. It's just expressing W on a log scale. All right, and that's what I'm saying here. S is just another way to represent W. The log W is just for convenience. But having said that, thermodynamics deals with entropy, not with W directly. You could redo all of thermodynamics, ignoring entropy completely, leaving entropy out completely, and dealing only directly with W, and you get all the right answers. It would look a little different. It would be probably a little bit less convenient to work with, but you could do it. It would work fine. So, but for 200 years now, we've been using entropy, so let's go with that. Another thing it's saying is that entropy counts microstates. If you know the entropy, you can calculate the number of microstates, right? If S is equal to Kb log W, I did this in the math review, right? Then W is equal to E to the S over Kb. So if you measure the entropy experimentally, which you can do, divide it by Kb, raise it to an exponential, and you can actually essentially experimentally measure how many microstates there are. So you can use the entropy to find out how many microstates. Entropy counts the microstates available to the system in effect. Yeah, and so I just say entropy is microstates effectively for all intents and purposes. Also, and this gets back to some of the stuff I set up above, that if W increases, and remember, if W increases, then that's the signature, that's the rule for when a spontaneous process will occur, then entropy also increases, and so conversely, if entropy is increasing, then W is increasing. And therefore, the second law of thermodynamics could be written that a spontaneous process occurs when W increases, or it could be written that a spontaneous process occurs when S increases, and in fact, we do say that, of course. The second law of thermodynamics is usually expressed in terms of entropy. Third or fourth or whatever point we're on here now, entropy always goes up when stuff can spread out. So in the boxes above, when V got bigger, when the volume available to the system gets bigger, when the system is less constrained, when some of its degrees of freedom increase in size, when their range increases, then entropy goes up. W goes up and entropy goes up. And therefore, the process will be spontaneous. And again, that's an expression of the second law. All right. So now we've got entropy. Let's do a calculation. Here we have our system. It's got a volume V1 on this side. We already saw that we can write the number of microstates in this case. It's V1 to the nth power and the number of particles divided by n factorial. And we now have the Boltzmann relationship, which says that S is equal to KB log W. We will also calculate a second W for a different volume, presumably a bigger one, when we've taken the barrier out, and we can calculate an entropy for that case. We can do it in the following way. We calculate the change in entropy. That's going to be S2 minus S1, or KB log W2 minus KB log W1. And using the properties of logs, that's KB log W2 or W1. This is all a homework problem, so you should get a good score on that homework. I'm basically showing you how to do the homework here. And if I plug in these definitions for W1 and W2, do a couple steps of algebra, that becomes KB log V2 over V1 to the nth power. And then using the property that the power comes down here, that's N times the number of molecules times KB times the logarithm of the ratio of the two volumes. And it turns out that the number of particles times, actually this is wrong the way I have it here. This should be NR. The number of particles times the Boltzmann constant is the same thing as the number of moles of particles times the gas constant. Let me just reiterate that. Avogadro's number times the Boltzmann constant is equal to the gas constant. So anyway, so that means this is true. This relationship is something we will derive in a few lectures from now, I think, from thermodynamics purely. We've just derived it from statistics. For this very simple case, we'll derive the same expression, exactly the same expression, using thermodynamics, using the rules of thermodynamics without a reference to statistics at all. We won't even mention statistics, and we'll still get the same answer. And what that's telling you is that the rules of thermodynamics at root are statistical in nature. The statistics are kind of hidden in thermodynamics, which is unfortunate, but that's because thermodynamics was developed in the 19th century before anyone knew about all these statistical interpretations of entropy. And so it wasn't formulated that way. And it's still not taught that way for the most part, but the relationship is there nonetheless. All right, so we've been able to calculate a thermodynamic quantity from a purely statistical understanding of what's going on in the process, and we'll come back to that when we start doing the thermodynamics. I guess there is one thing worth saying also before I go on to case 2 here, and that is that look what happens to the change in entropy. Look what this formula is saying. Look what happens to the change in entropy. This is what we have now. Let's see, nR log V2 over V1. When the volumes start changing, so if I say V2 is equal to V1, which means nothing's happened, right? I have this barrier in here. I don't take the barrier out. V2 is equal to V1. This is 1. Log of 1 is 0, and the change in entropy is 0. Of course, that makes sense since we didn't do anything in this case. There can't be any change in entropy if we didn't change the system. Let's consider a case where we move the barrier over a bit. So now V2 is greater than V1. That means that V2 over V1 is greater than 1. The logarithm of V2 over V1 is therefore greater than 0, which means that the change in entropy is positive. The entropy increased. That makes intuitive sense. Everything is agreeing with what we hope a good definition of entropy would do. On the other hand, if we move the barrier the other way, if we compress the gas, then V2 is less than V1. The ratio of the two is less than 1. And that means the log of V2 over V1 would then be less than 0, a negative quantity. That means delta S is negative. That means the entropy decreased. If we compress the gas, we're decreasing the available freedom, the available range of freedom to the degrees of freedom in the gas molecules. And therefore we're decreasing W, therefore we're decreasing the entropy. Okay, let's look at case 2. So that's enough about case 1. We've hopefully understood at least a little bit about what's going on in that case. Let's look at case 2. This is, at first glance, a completely different case. We've got an H atom here, a chlorine atom here. They're going to combine to form an HCl molecule. We know intuitively that that's going to happen. It is important, before I go further, to point out that I deliberately have here something called a T-bath. That means out here there's a lot of stuff. That means these walls here are not insulating. That means that energy can flow out to the surroundings, and that's really the key feature of this whole example. And to help illustrate that, let's consider what happens if we do put insulation. Now, it doesn't matter what's out here. We can have a T-bath out here, right, but we have perfect insulation. I'm saying it's ideal, perfect insulation. It stops all flows of heat. What happens in that case? Well, now no energy can pass into the system, right? There's no mechanisms by which energy can go from the system itself here to the surroundings out here. And that means energy has to be conserved within this system. So in that case, does this reaction go in this case? If we have this ideal case, now it's very hard experimentally to achieve these kind of conditions, so maybe your intuition isn't so clear. But let me tell you, the reaction really can't go in these cases. Why not? Well, momentarily the H could come together, the chlorine could come together, and form the HCl molecule, but the energy has to go someplace and it's got to stay in the box, which means that sooner or later that energy that you got, that you released, when that bond, that chemical bond was formed, is going to come back, and it's just as big as it ever was, which means it's sufficient to break that bond again, which means that you really can't form a permanent molecule in that way. You can get some transient bond formation here and there, but you can't get a stable molecule that way. It's going to come back apart because the energy didn't go anywhere. It didn't lose any energy. The energy, I mean, to think of it in mechanical terms, this is probably a good thing to do. Let's go over here. Here's our H. Here's our Cl. They start to get close enough, they start attracting each other, right? That means there's a force acting that's pulling the two together. That means that these two guys are going to accelerate towards each other, right? What's going to happen? Well, if there's no loss of energy, they're going to accelerate, they're going to collide, they're going to be stuck hard, but they've still got all the energy that they had when they were out here, so they're just going to bounce right back out. They won't form the bond. If there's some mechanism for getting rid of the energy, then they can lose that energy, and then the molecule will sit there and vibrate, depending on how much energy it kept and how much it lost, but you will get a stable molecule. But as long as there's no mechanism for losing the energy, you can't form the bond. And that's what I'm saying over here in this case, in a rather more idealized way. So let's consider then the case where you have a box that isn't insulated, and you've got, a big system out here, the tea bath, which is capable of absorbing at least as much energy as is lost when the bond is formed, and pretty much anything is big enough for that. Then the system can come together, energy is lost to the surroundings. What happens to the entropy of the system now? So now we have the system here, we've got the surroundings out here. What happens to the entropy of the system? Well, we went from two free particles, both free to move around independently of the other, to one bound molecule that has to move as a unit. Intuitively, that seems to say that the entropy went down. The number of microstates available to this system actually went down. In fact, that's true. You can do a detailed calculation for this case, and you can show, but intuitively it's already clear that the number of microstates available to the system actually went down in this case, and yet we know it will happen. Why? Well, it must be this energy that went out here that's doing something. What's it doing? Well, it's going out into the surroundings, and what's it doing out there? Well, we don't know. It depends on what's out there to some extent. But I will tell you, here's a rule we'll talk about later, that whenever energy goes out into surroundings like this, the number of microstates available to the surroundings increases. And that means that the total number of microstates for both system and surroundings considered together, which is in most cases going to be just the number of microstates available to the system times the number of microstates available to surroundings. Well, the number of microstates to the system went down, but the number of microstates for the surroundings, went up. Did it go up by more or less than what this went down by? And the answer is, you have to do the calculation to find out, but the answer is that this guy wins. This guy went up by more than this guy went down, which means that the total number of microstates to the whole universe, system and surroundings, actually went up. And since entropy is just a logarithm of this, if this guy goes up, then the total entropy had to go up too. The system entropy went down, the surroundings entropy went up, but this rise was bigger than that decrease, and so the total entropy of the system, of the universe, went up overall. So the second case is really not very different from the first case. In the first case, matter was spreading out, and the number of microstates was therefore increasing. In the second case, it's energy that's spreading out into the surroundings, and therefore the number of microstates, the total number of microstates everywhere, also went up. That's the second law of thermodynamics. I imagine that people are seeing, when you see things like this, when you talk about the entropy of the universe rising and so on, people are getting all kinds of remembrances from earlier classes where we talk about the fact that the second law says that the total entropy must increase, and that's true. All right, I said this twice already, but let me say it again. These two cases cover all the possibilities. This is here's the real statement down here. The rest of the class will be A, clarifying the ideas that I just outlined. There's a lot of rigor that I've left out. We'll get a little bit more of that rigor in the next section of the class. Working out the implications of these ideas, a lot of that, because there's a lot of implications, and then finally applying them to cases that we want to understand. All of thermodynamics is contained in these two examples if you really understand them. And I said this already, but let me say it again. Thermo is really simple at the most basic level. If you are a little unsure how these ideas all work out, I would encourage people to go over the notes, thinking carefully about it as you go. Maybe even re-listen to this lecture, but going over the notes is probably enough, probably even better. Spend your time understanding how these things work and what I'm saying, and that will serve you well for the rest of the class. All right, the next thing I want to do, I think actually what I'll do is stop here and we'll do these examples next time. That will be a fairly short lecture, but that's fine.